A very good morning to all of you, and uh, I hope everybody is fine. And I'm going to deliver a presentation on a philosophical foundation of quantum mechanics. And in this in this presentation, rather it will be a presentation that I'll be discussing with you, because we have a complete course on philosophical foundation of quantum mechanics in your semester 7. Uh, so I thought that let us have some part of this course in terms of a PowerPoint presentation. So uh, basically, this course is for those people uh, uh, who have not physics as their core subject. This course is only for those students who are from different branches of science and social science, and uh, and the number of students that we have in GE and OE, that number is maybe that number is not too large. Now, whatever that number is, what is important is that I would like to introduce you with some basic idea here in this PowerPoint presentation. So so this is you can check out this slide, and it talks about the classical mechanics. And I'm again repeating that this thing is for those students who are not from physics, and maybe even it might be of some use to the students who are in the main course in this university. But exclusively this course is for non-physics students. So if we go back we can broadly classify physics into two parts, and one part of the physics is Newtonian physics. We call it in general we call it as classical physics, and the other part of this physics is what is generally called as quantum physics. And there is some part of physics which bridges, it has some kind of bridge which acts as the starting point for full formalism in quantum mechanics, and where intuitively a long range of classical ideas are inculcated. Now, what is this domain? So we have broken this part into the two big categories. One is the classical part, and the another is the quantum part. But in classical, for classical, we have an extra part of the classical physics, what falls in the domain of special theory of relativity and general theory of relativity. And similarly, we have an extension of basic quantum mechanics, its extension to the quantum field theory, as like of the things that you have a range of courses in that. But what's the most fundamental point here is that what is the core, the basis of the classical mechanics. And what we say that classical mechanics, it's a branch of the physics that deals with the motion of the objects and forces that are acting on these objects, the trajectories that these objects have, the motion they have, and how we can predict the future of a motion if we know the initial state of that motion. And the historical, if we go historically, the science overall boils down to some basic philosophers. I will not go into the domain of those philosophers like the versatile Aristotle, Galileo Galilei. They really had their portion, and there might be the pupil of whom we don't even know the names who might have contributed to the field of science. but if you have to sprinkle the glitters out of the mud, then certainly you have some of the personalities that have given a relevant philosophy in the domain of science. And, and that's why I have chosen a situation that starts from Isaac Newton and the development of this classical physics. Let's make that as a starting point, even though that cannot be the starting point. They have to have a long range of people who have contributed to science in different capacities, in different domains, in different environments, and so on and so forth. Now, so if we talk about the Newton's laws, there are two kinds of things. One is the law of gravitation, which simply tells us that you cannot have matter where you cannot find an attraction between the matter. So what we call as universal law of gravitation, that means there always exists a force of attraction between the matter. If the two matters are at some distance with respect to each other, there is always a force between these bodies. And this is what is our universal law of gravitation, and gravitation governs. It governs the motion of planets. It governs the motion of the satellites that are moving around. They're moving around the Earth. The artificial satellites or the natural satellite, which we commonly know as the moon. So there are other planets, and you can certainly have an understanding of the motion of those satellites around the planets, and at the same time, the universal law of gravitation, it works well even in the modern world. It works well in the solar system. And the Newton's laws, we have conservation of energy, and then we have conservation of momentum, like shooting a bullet with a gun. If I have a gun, I'll shoot a bullet. The bullet will move with some velocity. It will have some mass. The product of mass and velocity will give us the measure of the momentum of this bullet. And if you have an isolated system, in an isolated system, this momentum of the gun and the bullet, it should be conserved. So what does that mean? That means if you shoot a bullet, it has some velocity, it has some mass. The gun also has some mass. So while shooting a bullet, what we do is we feel a drag that bounces us back, and that drag that we feel is because of the law of conservation of momentum. And conservation of energy, it can be extended from the ideal system to the overall universe, that the overall energy of the system remains constant. And you can see this photograph and things that we have here, like law of gravitation and the other laws of Newton. The law of gravitation precisely predicts the motion of the planets, motion of the satellites in the solar system. And if you have to be more precise when it comes to Mercury, because the precession of Mercury with respect to the rest of the planets in the solar system is more. It's more than that of the rest of the planets that are moving around the sun. That precession is an exception that cannot be explained using Newtonian laws, but there certainly the general theory of relativity gives us the precise prediction about the motion of the peculiar motion of the Mercury around the sun, and being it closest to the sun and falling into the gravity of sun. That gravity, when we choose that gravity as a wrapping between space and time, it precisely predicts that why the precession of the Mercury is more than that of the rest of the planets in the solar system. That we'll be talking about in the later case. So this is how things start, things start in classical mechanics, where things seem to be exactly predictable. You can predict the things, you can design the things, and you can articulate the future of an action with 100% precision. Now, there is another domain of this classical physics, and this domain is the domain of electromagnetic waves. I mean, sun is the basic source of energy for the planet Earth, and sun is radiating. It's emitting radiations, and it's not emitting only one kind of radiation. It's emitting a range of radiations, and these radiations can have different wavelengths, and they can have different colors, and these colors can superimpose, and you can have some resultant color. So what we have is we can see this photograph. We can imagine a thing like that the electromagnetic radiations that are coming to us, or that are moving in the space, they are a lump of different wavelengths, and some of the wavelengths can be observable, what we can see in this photograph, and there can be a long range of wavelengths which a human eye cannot see. For that, you need a different kind of eye. You need a different kind of sense, you need a different kind of sensors, by virtue of which you can detect those radiations. So sun is not emitting a single radiation. It's emitting a range of radiations, differing in their color, differing in their wavelengths, and so on and so forth. And what's the peculiar thing about these electromagnetic waves is that they spread. They have a property of spreading. They are continuous. There's no gap between the radiation. They happen to be exactly continuous in the medium and moving with the speed equal to the speed of light, what we call as what is nearly 300,000 kilometers per second, the fastest that we can imagine. And you can see that these the existence of the electromagnetic radiations are already present. Okay, they are coming to us, they are surrounding us. But it was James Maxwell who could compile the various basic laws of classical physics, the laws like Gauss's law in electrostatics, Gauss's law in magnetostatics. Then we have Faraday's law, what we call as, was generally known as Faraday's law of electromagnetic induction, and then we have Ampere's law. So it was James Maxwell who combined all of these laws, and he introduced a new parameter in the fourth equation, what we call as Ampere's law. He introduced a current. He introduced the concept of a current known as displacement current, and using those four equations, you can see the first one is the Gauss law in electrostatics, and the second is the Gauss law in the magnetostatics, and giving an indication that in classical domain the monopoles, the magnetic monopoles cannot exist. And the first equation is the Gauss's law, which tells us monopoles can exist. And then the third important equation, which seems to be the basis of modern electrical technology, by virtue of which the whole world is glittering. It's glittering with the radiators, it's glittering with bulbs, it's glittering with all kinds of things in terms of energy. The basis of that seems to be the Faraday's law of electromagnetic induction. And the fourth one that we can see here is the Ampere's law. And this Ampere's law was modified. It was modified by James Maxwell. And what he did is he modified this law and introduced the concept of displacement current. Because if you might have gone through secondary school physics that in a capacitor, if you have a capacitor, it has two plates. Between the plates there is nothing, or there is an insulation. There is a flow of current, but that flow of current cannot be independently described by the Ampere's law. So this current was defined and modified by James Maxwell. And solving these equations, the Gauss's law, the Faraday's law, and the modified Ampere's law, James Maxwell was in a position to predict these electromagnetic radiations. And it could be predicted that you could generate those electromagnetic radiations. So if you could generate those electromagnetic radiations, you could allow them to travel through the space. And it was the time when it was just predicted. It was not the reality of the science. It was theoretically predicted by James Maxwell. And later on, this philosophy of generating the electromagnetic waves, it was translated into the real technology. And I think the Hertz experiment was the first experimental foundation of actually producing these electromagnetic waves, and the speed with these electromagnetic waves could travel. They could travel with the speed equivalent to that of speed of light. And so the predictions, the arguments, the mathematical arguments of those times were translated into a pure philosophical arguments that were translated into a reality. And we can understand now that any format of communication that we have in the world, it has a basis of electromagnetic radiation. So you are developing better technologies to generate these electromagnetic waves, and these electromagnetic waves, they travel in all formats. They travel from telephones to mobile phones to internet. So they have their key role in all that format that we can see in modern science. And to me, I think the credit should go to the people that who devised those beautiful classical laws in electromagnetism: Gauss, Faraday, Ampere, and Maxwell. And they seem to be the people who have really given a strong contribution to the society in general, in terms of the mathematical formulation of those laws, which could later on be translated into the technology. And this technology is workable, and it's working in all domains of life. So the next thing, we can see that this classical physics, the Newtonian physics, it exactly predicts. It predicts, and these predictions are real to our day-to-day lives, where intuitions are alive, and it gives us the accurate predictions and predictions in everyday life. It gives us engineering of things, the engineering of cars, buses, planes, aircrafts, rockets, missiles. So it gives us the predictions about astronomy as well as, and there are predictions and there are applications, and these applications lead to engineering. These predictions lead to astronomy and different formats of life. And we can see in this format, you have a bicycle, you're swimming, you have the planets roaming around on some central body, and between two bodies there is a force, and that force leads to some kind of motion, and you can explain the motion of the planets, can explain the motion of the satellites, and uh, and the launch of the satellites could be precisely predicted with a good state of precision in the space. Now, the classical mechanics, there's a lot to tell about it. It doesn't, I don't find any border of classical mechanics where it cannot work. It has worked in all formats of our life. It works from cars to planes. It works in all domains. It works in all dimensions. But there's a breakdown. The classical mechanics breaks down. Where it breaks down at small scales. When the scale of the matter goes down to atoms, when it goes down to atoms, molecules, electrons, protons, neutrons, their classical mechanics, it fails, it breaks down, it's not able to explain what's going on at very, very small scales. This is one kind of breakdown which I may extend in coming future. And another breakdown is at high velocities. And classical mechanics, it fails, it breaks down at relativistic speeds. Now, what do we mean by relativistic speeds? I mean, speeds are there, a car is moving with some speed, a planet is moving with some speed around the sun, a satellite is moving with some speed. These are ordinary speeds. A speed that is close to the speed of light, we call this speed as relativistic speed, and that speed is the fastest. And why is it fastest? If the intuition is like that the light has the maximum speed to our intuition, it takes only 8 minutes for the light to come from sun and reach the planet Earth. So you can understand the distance between the Earth and sun is too large, and this large distance of the order of 10 to the power of 11 meters, I may be wrong, but to some approximation might be right. This much of distance is covered by the speed in just 8 minutes. And what classical mechanics has to say about it, that speed has no limit. I mean, you can have a ball that is thrown, a car that's moving, a rocket that's being launched, a bullet that's being shot down. They can have infinite speeds depending on the source, depending on the presence of force that can be exerted on these bodies. So if you can manage a force that gives a ball velocity greater than that of velocity of light, it's plausible in classical physics. It's plausible in Newtonian physics. But what we see in reality is there happens to have some changes. There happens to have some effects when we go into the domain of relativistic effects. The absolute nature of classical physics seems to be breaking down, and what happens in the Newtonian physics is that the mass of an object is constant, it's absolute. It cannot change whether this mass is at rest or this mass is moving with a speed 10 kilometers per second, or it is moving with a speed equal to that of speed of light. It doesn't matter in the domain of classical mechanics, because the mass is an absolute physical quantity. Similarly, the length of an object, if I have a scale like this, it has a length, and this is an absolute length of this scale. The length of this scale is not going to change if you allow this scale to move with any kind of velocity. So the velocity that you're giving to the scale is not going to change, it's not going to make any change in the measurement of the length of the scale. When you measure the length of the scale, it must be same whether the scale is at rest or the scale is moving with velocity that is far more greater than that what it is expected. So the length is so the dimensions of an object, they are an absolute physical quantity, and in whatever inertial frame of reference you're going to measure the dimensions of that object, they are not going to change. So so the dimensions of an object will remain constant irrespective of the speed of that object, whether that object is at rest, moving with some lower velocity, or moving with the highest possible velocity that is attainable for that object. And similarly, the concept of time in classical physics is absolute. So the time is not something that can change for a person in one frame of reference and for the person in another frame of reference. So whatever the case may be, whatever the frame of reference is, you are going to measure the same time. What does it mean? If I assume that I have some Roberts, and suppose I have 10 Roberts, and these 10 Roberts, they have say I have incorporated cesium clocks in all these 10 Roberts, and cesium clock is assumed to be the most accurate watch in the current times. And I send these Roberts in the space, and these Roberts move with different velocities. Some of the Roberts move with the velocities lesser than that of speed of light. Some of the Roberts move very close to the speed of light. And when all of these clocks will come back, and I will see all of these clocks, all the 10 clocks will give me the same measurement of time. This is what classical physics has to say about the time that's linked with the frame which is either in the rest or the frame that's in some uniform motion. So what you're going to observe is when all the clocks, when all the clocks will come back, I should see them all having same measurement of time. That's what classical physics predicts about these clocks, which is not the case. Here classical mechanics breaks down. So it breaks down in the domain of relativistic speeds. And again, talking about the small scales, when we talk about the small scales, we had different theories that have led us to understand the microscopic particles. And if I take the John Dalton as the starting model, so from here we have different postures of this atom, like we have the solid sphere model for an atom that was given by John Dalton in 1803, and then plum pudding model where you assume that the background of an atom is positively charged, and the seeds in a plum, they are equivalent to the negative charges. And then planetary model, assuming the same thing, trying to correlate the solar system with the structure of an atom, and assuming the planetary model, assuming that electrons are orbiting around the nucleus. And then Bohr's model, where Bohr's model is able to explain some of the important characteristics at the atomic state by postulating down some orbits in which electrons does not radiate. So what was the problem basically was that when we talk about the structure of an atom, if we go back to the Rutherford's model, it was Rutherford who discovered the existence of the nucleus in an atom, and that's why sometimes Rutherford is considered to be the father of the nuclear physics. But in his model, what he could not explain the stability of an atom. Why he couldn't do that? He couldn't do that because electrons have charge. And we were talking about the electromagnetic waves, and you could generate those electromagnetic waves when you could accelerate the charge. So if you have a charge, you accelerate it, you produce the electromagnetic waves. So that's the basic idea how electromagnetic waves are generated. Now the model that was given by Rutherford, this model in which electrons are revolving around the nucleus, these electrons have charge, and these electrons are moving in an orbit. If they are moving in an orbit, since they have a charge, and these electrons have acceleration because these electrons have different velocities at different points while having the circular motion with respect to the center of an atom. So what goes wrong here is that if this electron is accelerating, it must radiate. It must give out the electromagnetic radiations. So if it gives out the electromagnetic radiations, it must lose all of its energy and it should fall into the nucleus. So Rutherford, even though he becomes the father of the nuclear physics, he fails to explain the stability of an atom because electrons are charged particles and they are accelerating. If they are accelerating, they are producing the electromagnetic radiations. And these predictions are going against the experimentally observed facts, where when we see the spectrum of an atom, we don't find any continuity in the spectrum of the atom. At the same time, what we find is we find the lines, say for the sake of argument, line 1, line 2, line 3, and line 3. And here the genius of the Bohr comes in action, and where Bohr comes up with a beautiful argument. He comes with an argument of the angular momentum, which is equal to an integral multiple of n and h by 2 pi, where h is the Planck's constant. The second important argument is, come on, these electrons, they don't radiate. Why don't they radiate? He comes up with a postulate that the electron remains in those domains of this atom where the electron is not allowed to radiate. So this is the genius of Niels Bohr that comes in action and trying to explain the stability of the simplest of atoms. The simplest is of course the hydrogen atom. So proposing that electrons are revolving, accepting this reality, but at the same time putting a constraint, saying these are magical shells. I don't know why these things are happening. There's no explanation for them, but still these are the regions in which electron does not radiate electromagnetic radiation. So that means in all of these, so first, second, and third, they are trying to put the Newtonian mechanics into these microscopic domains, but the third one fails to explain it, and finally a different argument comes from Niels Bohr, and this argument gives a state of come on, okay, it can be stable. There is something fishy going on in an atom, and that's how there is some kind of stability. And finally, we have Erwin Schrödinger, and we see automatically, when we solve the problem of hydrogen atom, we automatically come up with the quantum numbers of the hydrogen atom, and we automatically lead that electron does not radiate at some particular parameters. So this quantization of shells it automatically comes as a solution of Schrödinger's wave equation on hydrogen atoms. So what's my point here is? My point here is that classical mechanics, Newtonian mechanics, it purely fails when it comes to the relativistic speeds It purely fails when it comes to the small scales. It cannot describe, it cannot predict anything about the microscopic particles, microscopic systems. Its predictions fail in that domain. So classical mechanics, it's purely intuitive. It fits with our human understanding, where we have a feeling of pull and push. Uh, those things which are quite intuitive to the human beings. It fits those kinds of arguments. But down the line, the things that are happening, they are happening extreme, and they are happening at extreme discrepancies. You cannot explain the things at quantum mechanical level. You cannot describe the quantum mechanical level by incorporating the Newtonian mechanics in those models. So I think today I'll stop here, and I'll take on this discussion in the next video. So I hope you'll find it, at least from philosophical point of view, you find that this introduction is in tone what you have come to learn here. Okay.